A single quantum chip recently finished a calculation in 200 seconds that would have locked a classical supercomputer in a cycle of processing for 10,000 years. How can a small piece of silicon and gold cooled to near absolute zero outperform a building-sized machine that consumes enough electricity to power a small city? This is the central question of quantum supremacy and the core of the title question: how a quantum chip solved the circuit before classical audits caught up. In the next 20 minutes, you will understand exactly how the gap between these two technologies has widened into a chasm that classical physics may never be able to bridge. We are witnessing a fundamental shift where the evidence of quantum power is no longer a theoretical prediction, but a measured reality that leaves traditional computing behind. The core spark of this change is not just the speed of the calculation, but the fact that quantum processors are now producing results that are mathematically impossible to verify using old methods. While a normal computer works with bits that are either 0 or 1, a quantum chip uses qubits that exist in a state of both at once. This simple difference creates a scaling problem for classical machines that is truly terrifying in its magnitude. One small payoff to understand right now is the concept of the exponential wall. Every time we add just one qubit to a quantum circuit, a classical supercomputer must double its memory capacity just to keep track of the possibilities. This means that while the quantum chip grows linearly, the classical auditor grows exponentially. And we have already reached the point where the auditor has run out of room. The default story we have been told for decades is that quantum computers are a far-off dream that will require millions of perfect components to be useful. In this old model, classical supercomputers like the Frontier or the Summit would always be the ultimate authority because they are reliable and predictable. We expected that any claim of quantum advantage would be easily debunked by a clever programmer using a more efficient classical algorithm. For a long time, this was true. When early quantum prototypes ran small tests, classical teams would quickly find a way to simulate the results on a standard laptop. This created a sense of security in the classical world, leading many to believe that the quantum threat was exaggerated, or at least decades away. However, this perspective ignored the hard mathematical limit of how information is stored in a quantum system versus a classical one. Contradictions to this old model are often dismissed as errors in measurement or noise in the system. Skeptics argue that because quantum chips are prone to mistakes caused by heat or electromagnetic interference, their results cannot be trusted. They claim that if a quantum computer cannot produce a perfect answer, it has not truly beaten a classical one. But this dismissal fails to account for a strange measurement result known as the random circuit benchmark. In this test, a quantum chip is asked to generate a pattern of numbers that is intentionally chaotic. For a quantum chip, this chaos is natural and easy to produce. For a classical supercomputer, simulating this specific type of chaos requires tracking every possible interaction between every qubit, which quickly becomes an impossible task. The first anchor contradiction occurred when the Sycamore chip produced a distribution of numbers that followed a specific quantum pattern called the Porter-Thomas distribution. This pattern is a clear signal of quantum behavior that a classical machine cannot easily spoof without performing the full, massive calculation. To understand why this is such a problem for our current machines, we have to look at the mechanism of a quantum circuit. When we talk about a random circuit, we are not just talking about random numbers. We are talking about a carefully designed sequence of quantum gates that entangles qubits in a way that creates a massive web of probability. The value of this test is that it provides a clean battlefield where there are no shortcuts for the classical machine. In a normal calculation, like weather forecasting or bridge design, there are often mathematical tricks that allow a computer to skip steps. In a random quantum circuit, there are no steps to skip. The supercomputer must brute force the entire state space. This is where the measurement limits of our best classical hardware become visible. To simulate 50 qubits, you need about 1 quadrillion bytes of memory. To simulate 70 qubits, you would need more memory than exists in every supercomputer on Earth combined. This brings us to the proof of the exponential wall. When Google first announced their results with the Sycamore processor, they claimed a 10,000-year advantage. This number was based on the fact that the supercomputer would have to store the entire quantum state in its random access memory. IBM, a competitor in the field, quickly responded with a reality check. They argued that by using a different storage strategy, involving hard drive space instead of just random access memory, they could reduce that 10,000-year estimate to just 2.5 days. While this was a significant reduction, it actually reinforced the quantum advantage rather than disproving it. Even with the best classical tricks and the world's most powerful supercomputer, a task that took a tiny chip 3 minutes still required days of processing on a machine the size of a basketball court. The stakes are clear. The quantum chip is operating on a level of efficiency that classical physics cannot match. As the hardware progressed, the classical teams did not give up. They developed a method called tensor networks to try and compress the quantum data. This is similar to how a video file is compressed so it takes up less space. By identifying parts of the quantum circuit that were less entangled, researchers could ignore some of the complexity and speed up the simulation. This was a powerful counterattack that showed many early quantum supremacy claims were narrower than people thought. However, this method has a built-in limit. As the quantum chips become better at error correction and can sustain more entanglement, the compression tricks stop working. The complexity of the system eventually exceeds the capacity of any compression algorithm. This is the moment where the hidden mechanism of quantum entanglement becomes undeniable. You cannot compress a truly chaotic quantum state without losing the very information you are trying to calculate. One of the most significant breakthroughs in this ongoing arms race is the development of the Willow chip. This new generation of hardware addresses the biggest criticism of quantum computing, the noise problem. In the past, as you added more qubits, the error rate would go up because there were more parts that could fail. Willow changed this by demonstrating that adding more qubits can actually lower the total error rate through a process called quantum error correction. This is a massive shift in our understanding. It means that we are no longer limited by the fragility of individual qubits. If we can build a system where more parts make the whole more stable, the path to a 1,000,000-qubit processor becomes a matter of engineering rather than a fundamental physics problem. This advancement makes the classical audit even more difficult because the results coming off the chip are no longer noisy approximations. They are high-precision data points. To verify if these results are legitimate, scientists use a statistical tool called cross-entropy benchmarking. Think of this as a lie detector for quantum computers. It checks the output of the chip against the expected mathematical distribution. If the chip is just outputting random noise, it will fail this test. If it is actually performing quantum gates, it will show a spiky pattern where certain bit strings appear more often than others. The difficulty is that as the circuits get larger, calculating what those spikes should look like becomes impossible for classical machines. We are entering a period known as the audit lag. This is the time between a quantum chip finishing a calculation and the classical community finding a way to verify it. Currently, this lag can last months. Eventually, it will become infinite, as no classical machine will ever be able to calculate the verification pattern for a 1,000-qubit circuit. This creates a strange situation where we have to trust the physics of the machine because we can no longer check its work using the old tools. This is what we call validation by proxy. Instead of checking the whole calculation, auditors check small subcircuits or simplified versions of the problem that they can still handle. They assume that if the chip gets the easy parts right, it is likely getting the hard parts right too. But this is a dangerous assumption in science. It highlights the missing signal problem. We are looking for proof of quantum supremacy in a regime where proof itself is becoming computationally impossible to generate. The evidence we do have, however, points to a clear trend. Quantum hardware is improving at a rate that far outpaces the development of classical algorithms. While a classical programmer might find a way to speed up a simulation by a factor of 10, the next quantum chip will be 1,000 times more complex than the last one. There is also a significant difference in energy efficiency that we must consider. The Frontier supercomputer, which is one of the fastest in the world, requires about 20 megawatts of power to operate. That is enough to power thousands of homes. In contrast, the cooling system and control electronics for a quantum chip like Willow use a fraction of that energy. The actual computation on the chip itself happens with almost no heat generation because it is a superconducting system. This means that even if a classical supercomputer could eventually catch up to a quantum result, it would do so at a massive cost in terms of electricity and time. This energy gap is a concrete trace of the different physical laws at play. One machine is fighting against the limits of classical thermodynamics, while the other is leveraging the inherent properties of the universe's most fundamental building blocks. Why is it that most people do not realize how close we are to this transition? It is partly due to the way these results are reported. When a classical team finds a way to simulate a quantum result faster than expected, the headlines often say that quantum supremacy has been overturned. But this is a misunderstanding of the process. Science is an arms race. The fact that classical machines have to work so hard to keep up with a tiny chip is the real story. The gatekeeping of this information often happens because the math involved in tensor networks and quantum gates is incredibly dense. It is easier to report on a simple win or loss than to explain the nuanced reality of a narrowing verification window. We are in a period of forensic intrigue where the traces left by quantum chips are being scrutinized by the world's best mathematicians, and the chips are winning. This leads us back to the title question: how a quantum chip solved the circuit before classical audits caught up. The direct answer is that the quantum chip operates in a mathematical space that is naturally high-dimensional, while the classical machine must simulate that space bit by bit. The evidence eliminates the old explanation that classical computers will always be able to find a shortcut to simulate quantum physics. The result that classical machines still have no account for is the ability of a quantum processor to maintain entanglement across dozens of qubits without the state collapsing into noise. While classical teams have used every trick in the book, from GPUs to advanced data compression, they are hitting a hard wall of memory and time. The mechanism that remains strongest is that quantum computers are not just faster versions of our current machines, they are. A different kind of technology altogether that uses the complexity of the universe as a resource. What this changes for your understanding is the realization that we are moving into a post-verification era of computing. For the first time in human history, we are building tools that can give us answers we cannot double-check using traditional logic. This requires a new kind of science, one based on the statistical consistency of quantum mechanics rather than the line-by-line verification of classical code. The verdict is clear. The old model of the supercomputer as the ultimate arbiter of truth is breaking. As we move from chips like Sycamore to Willow and beyond, the gap will only grow. We are not just waiting for a future where quantum computers might work. We are living in a time where they are already performing tasks that the most powerful machines ever built by humans cannot replicate or even fully understand in a reasonable time frame. In the end, the story of the quantum audit is a story of our own limits. We have built machines that can mimic the laws of the macroscopic world with incredible precision. But those laws are just a surface layer. Beneath them lies a much more complex reality of wave functions and interference patterns. The quantum chip is our first real tool for navigating that deeper layer. The fact that our classical machines are struggling to keep up is not a failure of engineering, but a confirmation of the incredible depth of the quantum world. The forensic evidence is in the bit strings, the cross-entropy scores, and the power bills of the supercomputers chasing the ghost of a quantum state. As we continue to push the boundaries of what these chips can do, the reverence we feel for the complexity of nature only grows. We are finally beginning to speak the language of the universe, even if we still need a bit of help from our old machines to translate the first few words. This journey into the quantum landscape is just beginning, and the distance between where we are and where we are going is expanding every second. If you want to stay at the edge of these developments and see how the next generation of detectors and processors will continue to rewrite the laws of physics, make sure to follow the progress of these experiments as they happen. The transition is not a single event, but a steady accumulation of results that the classical world can no longer ignore.